the wave changes mediums, it can change directions. So I'll pull that up. Once I flip this back to mirror. With all kinds of waves, the sound, but also light as we transition. So you can think of somebody needing help at the beach. They're in the water drowning over here. Help, help. And the lifeguard sees them. So we've learned that the fastest or the shortest distance between 2 points is a straight line. So this just simulates, you can a lifeguard can run fast, fairly fast on a beach, at least compared to with swimming. You can go faster here than in the water. So if we hit start, you can see it goes quickly, but once he gets to the water, or she, the swimming's takes a little longer. So this will give us the total time to get to the person to save them. About 11.5 seconds in this scenario. So the shortest distance between 2 points is a straight line. But we can do better. This one's based on how fast the lifeguard can get there. So how should we adjust things? Stay on the beach longer. So this is where, let's run on the beach because you can go fast here. Now you do have to run a longer distance on the beach, but you can go faster. So let's get to there, and that would be the shortest distance, right, in the water. So we'll run that one. So yeah, a lot faster. We got to the water, still pretty good. We do slow down, but it's a shorter distance. Do you think this will beat 11.55? Yes. Yes, yes. Just for a comparison, let's go this way. Quick, but oh, now we got that long distance in the water.
But what if the lifeguard was Michael Phelps? Does that make a difference?
Well, this would all be relative. If the lifeguard was Michael Phelps, every scenario would be quicker, but they'd all be the same relative for if it stayed Michael Phelps. So yeah, that one took forever. Well, yeah, Michael Phelps would still run faster on land than he can swim in water. But he can swim in water faster than most everybody else. So. Now, who knows? You grew up on the beach. You might be able to swim faster. You can do it in a nice calm pool, right? I don't know. In the ocean's a little different. Well, here's something interesting. There's a balance. That this is not the quickest. It's quicker than this, and definitely over here. But let's see. I already found it for you. Right there. And it's because, yes, you can go faster on the beach, but you don't want to go too far on the beach. So let's see what this comes out to be. Oh, yes, we get some, about 11 seconds. We cut a half a second off, a quarter of a second off from this case. So this is refraction. There. So it's coming in, it comes in this. If it didn't refract or bend at all, it would just continue straight like that. But remember the wave front. You can think of the waves perpendicular like this. It is faster and gets ahead, so it turns. And that's what happens. Waves follow the path of quickest time, of least time interval. That's what waves do. Sound waves as well as light waves, and including lifeguards on a beach. That would be the quickest way to get to the person needing help. So maybe that would stick in your brain a little more to help remember what refraction is. Questions? Yes? Sound and light are not on the same spectrum. You're thinking of the electromagnetic spectrum? Correct, they are not. Because they're different types of waves. Sound is a mechanical, longitudinal wave. Light can self-propagate by itself and is transverse. I'm only aware of the electromagnetic spectrum. And then it has lots of different ones in it, which I hope to get to today. Sound, we just call it sound. Now, why they don't call it a spectra, I don't know. It literally is a spectra, because basically a spectra just means it has different frequencies. You know what? Let's just pull it up now. We're on it. I think I put it here. Here's the electromagnetic spectrum, right here in the middle. We're used to the visible light right here, which is, by the way, I wrote this down, 1/1,000,000th of 1% of the known electromagnetic spectrum is light, visible light. 1/1,000,000th of 1%. So that's a teeny, teeny, teeny amount. That's our colors: red, orange, yellow, blue. And what's different in these? The frequency, the wavelength, the energy. They're an electromagnetic wave. They're a transverse wave. You can picture that. They vibrate back and forth and travel through space. Red light over here, this is the wavelength. It's 700 nanometers. That's a billionth of a meter. Yeah, billionth. Purple on this side is 400 nanometers, so the waves are shorter. The wavelength is shorter on the purple. So which end do you think vibrates more quickly? Yeah, the small waves, just like we've done with sound waves. This has higher frequency, shorter waves. Red, longer waves, lower frequency. The associated energy here is greater with purple because they're vibrating more quickly. That's the only difference in the spectrum. The exact same type of wave, they're just vibrating at different rates and thus have different sizes and energies. So, if you look at infrared waves, I'm sure you guys have all heard of those, we can't see them, but they're just over here, they're shifted. They're like beyond the red, infrared. So they're even bigger waves that vibrate more slowly with less energy. Then you get into radio waves, even bigger, huge waves. Now I want to note, radio waves are an electromagnetic wave. They're a form of light that we can't see. That's how you pick up your radio station. That's how the signal gets to us, the disturbance to us. That's different than sound. Sound is what we hear. That's what comes out of your speaker. You get reception through an electromagnetic radio wave, but the sound that comes out is not a radio wave, it's a sound wave. You understand the difference? Some people get confused between that. What I'm saying is sound waves.
If radio waves were sound waves, then wouldn't we hear like sound around?
Yeah, because there's radio, that's right, we'd hear it. Radio waves are around us all the time. Actually, the electromagnetic waves are going on all around us. You know, smartphones. You got your data on? Well, that's picking up an electromagnetic wave. You're using Wi-Fi instead? Well, the router's right under there. It's broadcasting, and that's what's picking it up. That's an electromagnetic wave. It's just a form of light we can't see, vibrating at a lower frequency, bigger waves. Microwaves, you know, that you actually cook with, they actually emit microwaves. Those are, they're not on this spectrum. They're over here. They're a type of X-ray. Over here, they vibrate quicker. They have small wave. Wait, am I saying that right? It's irrelevant at this point. It's an invisible, my point is, it's an invisible wave that vibrates at a different frequency. And it actually sets up standing waves inside your cavity. They reflect off the sides and come back. They hit resonance, and they make the water molecules start vibrating because it absorbs that energy. When they start vibrating, creates heat and heats up your food. Black lights, ultraviolet light, X-rays, when you go to the doctor and they image you, they can pass through your body, but the bones absorb them, so you can get an image that way. Question? Well, this end of the spectrum, gamma rays, they have the shortest wave, thus the highest frequency, and the most energy. So they can damage you, our tissue, just like X-rays can if you get exposed to them too much, or microwaves. Think of that, if you absorb them, or they have an interaction with you, energy is conserved. They have more energy, so it's going to put more energy into you, and that can cause damage. But that's a spectrum. Why we don't say there's a sound spectrum? We don't label it. It's just because it's easier for us to think of, oh, la 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 la. You know, there's a spectrum, an octave. It's a range of frequencies. Low frequency, high frequency, an octave apart. So that was a long-winded answer, but to help me teach other things. Anything else you want to add to it? Okay. Any other questions? Yeah.
Think of sound more solely based on frequency of things with light, but it doesn't change its properties, whereas with sound it's pretty much is a lower higher frequency, it's not going to really change.
Actually, I'm going to merge that even more. You're saying sound and light. You can think light is light, sound is sound. The only difference between different sounds is the frequency and the wavelength. Pure sounds. You can add a bunch of different types of sounds together and create a funky looking waveform, but the individual frequencies are just different sized waves with different energy. La, la. Longitudinal wave, mechanical wave. Light. Ultraviolet, infrared, your black light that makes things glow in the dark. Just different frequencies, different size waves with different energy. They're all the same. We can just only see 1/millionth of 1% of the entire spectrum. So all these forms of light reflect, refract, superimpose, Doppler effect. So it can all happen. Okay. The Doppler effect does it because it happens with any wave. That's what I said, how they can tell how fast a star is rotating. Because if the light on one side is going away from us, while the light on the other side is coming towards us, they can actually detect the shift in the wavelength and the frequency. And how much it shifts tells us the Doppler effect. Just like if the car is coming fast, you hear a big shift, right? If it's going slower, it's more like there's less of a shift. Yes, you'd have to be going really fast, like a third of the speed of light or something. Stars are binary stars or something, yeah. Yeah, for us to see like my favorite bumper sticker. I didn't pull up my image. Let's see if I have it here. What the heck? What do you mean, no? Okay, quit. If I find it real fast, I'll just pull it up. If it's on my computer here. Nah, it didn't look like it. Oh, wait. Sweet. Okay. My favorite bumper sticker. If it's a red sticker, if the sticker is blue, then you're driving too fast. So in theory, it's on the back bumper, and you're speeding up, and you're going to run into them. Well, this could happen, theoretically, because red light's coming to your eyeball. You're in the speeding car, and you see red. Well, if you're approaching, what happens with sound if you're approaching? Which way does it shift? Does it increase frequency or decrease frequency if you're coming together? As it's coming at you, it increases. Remember, the wave fronts are getting smushed together. The waves are smaller, frequencies increasing. Same with light then. So this red wavelength should be getting smaller and vibrating faster from our perspective. That would be towards the blue side. So if this sticker appears blue, then yeah, you'd be going pretty darn fast. The reason it's funny is because it'd have to be about a third the speed of light for that to happen, and we can't do that. But yeah. I calculated it once, and all I remember is something around that fast. But that'd be kind of cool to see. You could try that with the red stoplight with a police officer. Police officer, I know I was speeding, but I was going so fast the red light looked like it was green. Yeah, well, I wouldn't try it. Okay. While we have the things down, this is a good spot. Let's transition to clickers. Yeah, ask away.
So in like Star Wars, if they're going at hyperspeed, would the colors of the stars shift?
Yes. Like Star Wars and whatnot. Yeah, if you're going that fast, you'll see the light Doppler shift. So yeah, you can actually see colors change. So yeah, sometimes you see the little light streams, beaks, light streaks, light beams streaking. Yeah, and they're kind of colored like the rainbow. That could happen if you're going that fast. Oh, I don't remember which one of these I like. Let's just try. That's 2. I'll go with this. All right, let's I have started the session. Okay. Oh, geez. Bueno. This new operating system has trouble detecting these projectors. Yeah, it's up there, but it's not telling me it's up there so that I can mirror it to do it. Come on. Play nice. So, since I'm boring you, I'll talk out loud. Oh man. On a Mac, when you connect up, there's supposed to be a tab here that says Arrangement that I can click on so I can mirror, so we're seeing the same thing. And it's not showing up at the moment. Well, fine. I will just ask him to you. We're going to do it and see if that works. I only had a couple anyway. Because I still get your responses. I'll just have to tell you what the questions are. All right, first question. You guys just have to listen more carefully. Don't even need this then. I'll write the session ID for those of you that didn't see it and all my messing around. All right. When sound undergoes refraction, it undergoes a change in what? So when a sound undergoes refraction, it undergoes a change in what? And your options are for this one, A, B, C, and D. Frequency, wavelength, speed, or intensity. When a sound undergoes refraction, it undergoes a change in which one of these? What is what? Yeah, velocity. Yeah, we can always get around technology. All righty, 10. Get those answers in. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you thought it was speed. That is correct. It's this one. That's what causes refraction. It's because it changes speed when it changes mediums. If it didn't speed up or slow down, it wouldn't bend, it wouldn't refract. It changes direction, yes. Now, while we have that, velocity is frequency times wavelength. When it changes a medium, it changes velocity. That was the point of the question. So something else does change. Something else can change. Which one do you think it is? Think back to a guitar string. If I just hold it down in a different spot, I've changed the wavelength because I've changed the size of the string. Thus, the frequency changes. So if I change the wavelength, that changes. But that didn't change because I didn't change the medium. It's the same string. It's just shorter. The other case, remember, was I left the size of the string the same, but I tightened the string. I changed the tension and thus changed the properties of the string. And if it gets tighter, that increases, then that increased. We heard a difference. So one of these generally stays fixed and the other two adjust. So something does happen as a result. It doesn't cause refraction. The difference in speed causes refraction. But one of these has to give. If that is going to increase, then one of these has to increase. Which one do you think it is? Okay, we got one vote for frequency. Two votes for frequency. Anybody for wavelength? No? Let's reason this through. I try to get you guys to reason. Let's see. Let's look at light. That one might make more sense. If I shine red light through my glasses, didn't plan this. You know, if I shine red light through my glasses, what color will you see? Red. The light is vibrating. It doesn't change the rate at which it vibrates. So you'll still see red light. So it's the wavelength that actually changes. Let's think of an example with sound. If you're listening to your favorite song and you listen to it under water, or I don't know, I'm making this up. You'll still recognize the song. Yes, it'll be muffled and all that kind of stuff, but it'll be the same song. It's still trying to vibrate. The speaker, under the water is still trying to vibrate at the same rate. But the waves that come out will be slowed underwater and change the wave fronts. They get smushed together. So now you know. This is what causes refraction. And going back to our relationship, then one of these has to change. And now you know it's that. Let's look at it this way again. We got a wave coming in. If it slows down, like from I haven't gotten there yet. I won't. Let's say it bends towards the normal in this case. That angle is less than the incoming angle. Let's look at a wave front. Again, normally it'd be like right here. Which one is going faster? Up here. So it's going to get ahead while this one stays back. You can see it's going to turn that way. Think of the wheels on the axle. This one will slow down, and so it's going to, once it gets to there, this one's going to slow down. Slow down. Slow down. And eventually you're in the water, and now they're closer together. Maybe is another way to look at it. This distance is farther apart. The wavelength has now changed. It's closer together. It still goes up and down at the same rate. The frequency stays the same, but the speed that it's going to get through is more slower. Because it's the speed, well, that's what caused it. Because the speed is slower, it turns, changes direction. That's what we call refraction. Can you see the wave fronts getting mushed together because it does that? It'd be the opposite if it's coming back out. As it sped up, they'd spread back out.
So is it when the velocity decreases, the wavelength decreases? And when the velocity increases, the wavelength increases?
That's correct. This one is slowing down as it goes through here, and they get closer together, and vice versa. Right, that's why I stopped saying air and water. This is a generic example. So, yeah, you don't know what these are. So yes, for sound, it would be going from water to air. Ironically, light, this would be air to water. And we'll start discussing that. I'm not there yet. No, one more question then. Let's go to... We talked about this before. Okay, polling's open. And let me write the answers down here. Sound normally travels farther in air when the sound is what? Which of these? Low frequency, high frequency, resonant, and low in energy. Sound normally travels farther in air when the sound is which of these? Which of these allow it to go further? Sound normally travels farther in air when the sound is? Which of these cases allows sound to travel the farthest? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Overwhelming on low frequency. That is correct. Why? Who remembers? Well, 65% of you remember. What are you thinking? You cross those. He was remembering the example of FM with AM. Which one's highest frequency? FM is higher frequency, megahertz. AM is in kilohertz. So FM has a higher frequency, and it doesn't go as far. The lower frequency AM goes further. Why, though? The wavelengths are greater for AM, true. What? Energy. Yeah, it's going to stop traveling if its energy is dissipated. The one that has more interactions, that's vibrating more quickly, is going to have more interactions. Every time it has an interaction, energy is transferred to the medium for sound, and so it dissipates. So high frequencies, lots of interactions, energy transferred, and it doesn't go as far. It's going to poop out before a longer wave would. Yes? Yes. Yeah, ham radios operate on a specific frequency. That's right. They can, and based on the frequencies, how far or well they will travel. All right. You can put your clickers away. I'm going to attempt one more thing here. This is what an electromagnetic wave looks like. Just bring one down for now. So the yellow you can think of as an electric field. It's varying. Look at the y-axis there, that y arrow. You can see it. It goes up and back down, and then increases in the opposite direction, back to zero, more positive, less positive, more negative, less negative as it goes up and down. There's a magnetic field doing the same thing, perpendicular or transverse to that. They actually drive each other. The change in the electric field drives the magnetic field, and the change in the magnetic field drives the electric field, which allows it to self-propagate without a medium through empty space at the speed of light, because they're conserving energy. It's a constant speed. But the entire electromagnetic spectrum looks like that. You just change the size of the waves or the frequency, how fast or slow they're going up and down. Is this what constructive interference looks like? No, this is not showing that. This is just showing the oscillating E and B field, electric and magnetic field. This is no different than us wiggling the spring. Part of the spring goes up and down, but the wave looks like it goes side to side. It's a transverse wave. And you can see, just pick one of those arrows and it's just going up and down in place. That's the vibration. The wave travels through space. And again, the source of all waves is something vibrating. What creates light is a charged particle has to be moving somewhere. Picture an electron. If you make it go like this and vibrate back and forth like in an antenna or a transmitting antenna station, then there's going to be a corresponding electromagnetic wave that's propagated out into space. So this is just two components, the electric field and the magnetic field. In this case, they're in phase with each other, which we call constructive interference, if that's what you're relating to. They're always that way. Yeah, in that representation, the yellow was electric and the blue was magnetic, yes. So let's understand this frequency driving of things a little better. We did resonance. Remember the ruler vibrating? Everything wants to naturally vibrate at certain frequencies. Like this tuning fork. If I hit it, I drive it. It resonates. That's the frequency it wants to vibrate at. It's its natural frequency. Can you guys hear that at all? Can you hear it in the back? I'm curious. Well, I'm going to use this natural frequency of the tuning fork and force it to vibrate this box. So if they're connected, the tuning fork is now driving the box and moving the box. And the box forces the air inside it to vibrate. And that sound wave comes out and you can hear it. It's a sounding board. It amplifies the amplitude. I know that's redundant. It makes it louder. But it's the same frequency, it's the same wavelength. It's just driving it. Here's another version. Tell me if you can hear this. So little bumps on the cylinder go past little xylophone rods, and they go up and down, and so they flex just like that metal ruler did, and it vibrates at its natural frequency. Well, these have different lengths. They're like different length rods, so they have different natural frequencies, the notes of the song. To hear it better, if we could make this, like the tuning fork, make something else vibrate, we need to couple it to the air better, because air is how we hear it. That's how you guys are hearing it. So I like the board. Now when I do this, the little xylophone bars will move. They'll make the board move, and the board's big. It can push a lot of air around. And let's see if you hear a difference. Let's try it on this door. I love that. So we talked about guitars. He was nice enough to play the ukulele, pianos, violins. The strings make the vibration, the specific notes. But it's because they're attached to a sounding board that gets the air to move that allows us to even hear it. Remember, we had that wave spring up front. We wiggled that. It didn't make any sound. But remember the space phone? Once we attached it to a diaphragm and made the diaphragm move, then we could hear it. So it's the same like when you blow over a bottle. I'm forcing the air to go in and out. But this has a certain size. That determines the wavelength and thus the frequency, the note we hear. And it oscillates in and out, in and out. So it has a natural frequency that we can hear. This one's a bigger one. How do you think it'll sound? Lower. A bigger wave, which will vibrate more slowly. I always wanted to be in a jug band. But that's how it works. They are resonating at their natural frequencies. Remember we did tuning forks? If I make them vibrate at the exact same frequency, then they can drive each other actually. We didn't hear beats when they did that. But let me hit this one. I'll do that again. So this one wants to naturally vibrate at the exact same frequency this one vibrates at. So if any of the sound waves go into there, they make it. That's resonance. If they were different frequencies, it wouldn't work. Here they're the same. And like magic. The ping pong ball is just there to help you see that that one's moving. Yeah, Court? Yes. Anybody want to try? As long as you hit that frequency that it naturally wants to vibrate at. Now let's change the frequency. Now, do you remember what happens? Doesn't move as much. That's because we now have, it's in and out of phase. Every once in a while it makes it go, but then it messes it up. Makes it go, messes it up. Constructive and destructive interference.
Is that what you call beats?
This is beats. And that frequency of beats we hear is the difference in frequency between these two. That's how you find beats. So if the beat frequency is 2 hertz, then these are exactly 2 hertz apart. This could be at 400 hertz and this could be at 402 hertz. Or 398, as long as they differ by 2 if you hear 2 hertz beats. So let's use this resonance thing to start talking about how light goes through things. Transparent materials, like your glasses. Visible light gets through it. It's transparent to visible light. How does light do that? Light comes in, it doesn't need the medium. I have to emphasize a lot again. Sound was a mechanical wave. It needed the medium to vibrate in order to propagate. Light does not. It doesn't care. It actually wishes the medium wasn't there. It just gets in its way. Sees it as a hindrance, if you will, to get through. So light's traveling, it's happy, and now it enters the glass, and it comes out the other side, because that's how we can see through. We can see it. What's it do to the material in the glass? Think of this wave coming in. It's vibrating. It gets absorbed by a glass particle. Think of, I'm a glass particle. I absorb that energy. Bloop. The light is vibrating at a certain frequency. It's natural frequency. That determines whether it's red or orange or blue or infrared or gamma rays. It's got its natural frequency. Well, it hits me. What's it going to make me do? Start vibrating at that frequency. If I don't like that frequency, I tend to give it up. And the wave shoots back out on the other side. It's actually a different wave. The wave that comes in, I absorb it, makes me vibrate. I now have kinetic energy, but I don't like it, so I give it back up in the form of light. But it's the same frequency, so it's the same type of light, but it's actually a different light. This wave is not the exact same wave that comes out. But if it's red that comes in, it's red that comes out. Just like I said, if you shine red light through you, you see red. So here comes the wave, hits a particle, bloop, and it bloop, gives it up until it runs into the next glass particle. Bloop, it absorbs it, makes it start vibrating. It gives it up, bloop, until it makes it outside of the glass and it goes along its way at the same frequency. But again, this is a different wave than started over there. It has the exact same frequency, energy, and wavelength because of this transition through here. It had to interact. Remember with sound, the speed of sound was determined by interactions. The more interactions you have, the quicker it can get through. The speed of sound is greater with more interactions. So a solid, speed of sound is faster in a solid because it bumps into itself quicker. Light is delayed by the interactions. It takes time to do this. Bloop, 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 bloop. And each one of those interactions delays how long it takes to get through the glass. We say that light slows down when it goes through glass. Now listen up. Light, the speed of light's a constant, period, end of story. Between particles, it goes at the same speed. Bloop, shoo, bloop, shoo. It's outside of the glass, shoo, same speed. But do you see how it's getting delayed through the glass with each one of those absorptions and reemissions? That delay means it took longer to get through the glass. So we say it went slower through the glass. Does that make sense? So just like sound waves could change speeds when they go through things and refract, so can light. Because it effectively changes speeds. The average speed through it is different. The time is delayed. So that's why on this one, if this is light and this is air up here, it goes faster in air, and now it goes into the water, if this were water. The water molecules are closer together, they're more densely packed, and so it's harder for the light to get through. It has to interact with more of them before it can get through. So it's effectively slowed down, and it refracts. The way I drew this one was if this was air, that was water for light. Yeah, scientists in research labs can actually slow light down and stop it, trap it. Yeah, you might have heard of Bose-Einstein condensates. That's something very similar. Look at this one. Think of this as like the beam of light that comes in and it interacts with the glass. Oop, but this one came out. It's an identical sphere. It comes out with the same velocity as this one came in at. But it's not the same sphere, is it? Think of that when you're thinking of light going through something. The disturbance, the energy, the momentum is transferred through, but it has to interact. First to that one, that one, that one, that one, and that one. But sure, it does it quickly, just like this does. But it does take time to get all the way through. So let me draw a picture of the glass. That's a piece of glass. Here comes the visible wave. And it goes right on through. That's visible. Visible light goes through most forms of glass. It's transparent. And that's what we mean. It doesn't absorb it. It goes on, it's passed right on through. Ultraviolet light. Ultraviolet. Is that a shorter wave or a longer wave? Good. It's shorter, a higher frequency. So it looks like this. Most forms of glass get absorbed by ultraviolet light. I wrote that down. It makes the electrons resonate. This has a natural frequency. They hit the electrons in the glass, and they like vibrating at that frequency, so they absorb. It's at resonance. Lots of energy goes in. The amplitude gets bigger. It absorbs them. So they don't come back out. Glass is opaque to ultraviolet light. You can try it. Most forms of glass, if you have your black light and it's making something glow, put a piece of glass in between it and it'll probably stop glowing. Most forms of glass. Yeah?
So since the electrons in the glass are picking up energy, would that be seen as like temperature? Or
Very good. Very good. If they're absorbing that energy, he says, where does that energy go? It goes into making a move, but they're moving, and ultimately it warms up the glass because energy is conserved. Solar power, yeah, is absorbing radiant energy, an electromagnetic wave, and converting it to electrical energy. So we can use it. Infrared is even longer, and it gets absorbed also. Last thing I'll end with. It actually makes the molecules vibrate. This one resonates with the electrons. This one resonates with the molecules' natural frequency. So they resonate, the amplitude goes up, they absorb it. It's transparent to infrared also. Try shooting your remote control. Well, That one's kind of near infrared. It's better with long infrared. It would be more conspicuous. Maybe a bad example, but whatever. There was a question?
Oh, I was just gonna say when, like, they show, like, women screaming and then glass shatters, is that because they make the glass like,
Yeah.
the sound wave is the same?
In order to sing and make this shatter, I have to sing at the exact resonant frequency that this naturally wants to vibrate. When I do that, it absorbs that energy and can break. Have a great weekend.